So today we're going to discuss cross-sections and decay rates. So what we'll do is we'll relate the scattering amplitudes that we've spent the last few lectures learning how to compute to these two observable quantities. And along the way, we'll get some practice using the Feynman rules we discussed yesterday to compute scattering amplitudes. So the plan for today's lecture is, first, we'll learn how to compute cross-sections and how to relate them to scattering amplitudes. Then once we've done that, relating decay rates to scattering amplitudes is it's almost the same procedure. So we'll just discuss the few differences between the cross-sections and decay rates. And then we'll go over a few examples that will give us some practice, both in using the cross-section formulas and the Feynman rules from yesterday. Okay, so let's first go back to classical scattering and see how the classical scattering cross-section is related to the probability. So let's imagine we have a beam of particles. It's moving with some velocity v at some fixed target masses. So let's imagine the particles we're sending in are point masses. And we can imagine that the targets are, say, spheres of radius r. And these are at rest. Let's furthermore assume that these have some uniform density rho b, and the targets have a uniform density rho a. And it'll be convenient just to assume that these are distributed just over some distance LA, and these are distributed over some distance LB, which can be related to the velocity and the time it takes the beam to pass a particular point. And the last thing we need to do to compute the probability is we need the cross-section of the common to the two beams. And so let's denote that by A. So A is the cross-section common to the two beams. Okay. So classically, the number of collisions is sigma rho A LA rho B LB A. So you might be able to guess this based on dimensional analysis, but I'll explain it in a little more detail in a minute. So it should, the number of collisions between particles of the two types should be linear in the cross-section, should depend on how big the cross-section of each of the particles are, and the only way to make the units work out are to put in, well, it should also depend linearly on rho A and rho B, so make the units work out, we should need the factors of LA and LB. But we can understand this in a different way. So we can also, say, compute the fraction of the area that is covered by the particles of rho A. So we can imagine that, say, these are rain droplets, and we've got some rain barrels uniformly distributed along the ground. So the probability that one raindrop will land in a rain barrel will be equal to the number of rain barrels times the fraction of the area where it's raining that each rain barrel covers. And so then the total number of collisions will just be equal to the number of raindrops times the fraction of the area that the rain barrels are covering. And so then all that's left to do is compute what NA and NB are. So NA we can also write as rho A times the volume, which is just LA, A, and similarly for NB. And so we can write this in another way, using the fact that the volume is just LA times A, or LB times B. So we can write this also as sigma NA NB times VT over the volume. And then the probability of collisions is just the number of collisions divided by NA and B, which is sigma VT over the volume. So classically, that's the relationship between the probability of collisions and the cross-section. T is the time it takes for the beam to pass a certain point in this frame. And so we can compute the probability given the amplitude. And so we can just demand that this formula holds in the quantum theory so that the relationship between the probability and the cross-section is the same in the quantum theory as it is in the classical theory. And so we're going to use this formula to figure out what the cross-section is. So to do that, first we need to think a little bit more carefully about what the probability of collisions is in the quantum field theory. Clearly, it's related to the scattering amplitude that we've been considering, but let's write that out and see what the formula gives us. So Q of T, we're interested in 2 to n scattering. So it's extremely unlikely that we'll have 3 particles collide. So 2 to n is the most interesting case. And so we want to consider initial states with 2 particles. I'll denote the initial momenta with k's, and final state, which has n particle, will denote the momentum of each of the final state particles with a p. And so for a fixed final state, the scattering amplitude from this initial state to this final state will be infinitesimal. Basically because there's almost always continuous parameters, or there's always continuous parameters in the final state. So if we have, even if we're just considering 2 to 2 elastic scattering, there's the angle at which the final state particles goes out is undetermined. And So if we just ask the question, what's the probability that we have 2 to 2 elastic scattering and the final state particles go out at some particular angle, the answer is going to be 0. So we need to integrate over the final state momenta to get something finite. So better question to ask, so what's the probability that this initial state will scatter into this final state is what's the, we need to ask what's the probability that this initial state will scatter into the integral over the final momenta of final states, say, with this number of particles. So what we can compute directly is the differential probability, which is related to the scattering amplitudes that we've been computing. But if you remember, we did not unit normalize our states. So we chose a relativistic normalization. So this is not a probability. We need to normalize this in order to account for the fact that our states are not unit normalized. So we should divide by the FF and II to properly normalize our initial and final states. And then finally, we should have a measure over here. So we should integrate over our final momenta. But this equation, as written, must be missing something. The probability is dimensionless. This ratio of amplitudes is also dimensionless, whereas momentum has dimensions. So the correct way to make this make dimensional sense is to insert a factor of the volume here and 2 pi cubed. And so why is this the correct measure? So we can think about what would happen if we ask the same question in periodic space. So in periodic space, with a volume all cubed, the momenta will be quantized. So we can write Pj as 2 pi over L times Nj, where Nj have integer components. And so the correct thing to do in that case would be to sum over the final momenta. And if we go from a sum over Nj, then using this relation, that would become an integral d3 pj times the volume over 2 pi cubed. So that's where this measure comes from. Okay, so let's see what we can do with this formula for the differential probability. So let's look at the pieces one at a time. So first, let's look at the numerator. So the numerator, Fsi squared. For scattering processes, we can write this as 2 pi to the fourth delta to the fourth of total momenta, or using p for the final momenta and k for the initial momenta. So let's write that out. And then we have the matrix element squared. So FSI is related to the matrix element like this, and we're squaring it. So we've got the matrix element squared, which is fine. But we also have this delta function squared, which is concerning. In the front end, we told you that the theory of distributions is linear. So what does it mean to square a delta function? So we can interpret this as follows. So we can write the square of the delta function as 2 pi to the 4th times delta 4 sigma pj minus k1 minus k2. And then the second delta function is just delta of 0. You can use one of the delta functions to just set the arguments of the other delta function to 0. And this is the same factor that we interpreted earlier as just the volume of space-time. So if you remember back when we computed the ground state energy of the free Klein-Gordon theory, we ran into a factor like this. And the resolution we took then was that we could write this just as integral over space of e to the I times 0 times x, which is just the volume of space-time. So it's just the volume of space times t. Okay. So that's the numerator. So we see some factors of volume and t, like we had in our formula relating the probability to the cross-section. Now let's look at the denominator. And so recall that our one-particle states are not unit normalized. We normalize them in a relativistically invariant manner. The normalization we chose was this one. And so if these were different states, if this was, say, k and p, we'd have a delta k minus p here. But if this is just the norm of the one-particle state, we've got the same momentum in the bra and the ket, and we've got a delta of 0, which we can interpret in the same way as this 4-dimensional delta. So this is just, you can interpret this just as the volume of space, of 3-dimensional space. Okay. Sorry, with the 2 pi's. So it should be 2 EK times volume. Okay, so the same logic tells us that the norm of the initial state, which is a 2-particle state, just is 2 EK1 to EK2 times the volume squared. So we'll get one factor. So basically, if we're going to compute this, we just use the commutation relations twice, each time getting a factor of 2 pi cubed 2 EK delta of K1 minus K1 or K2 minus K2. So we get 2 factors of the volume, 2 factors of the energy. And similarly for the final state, we just have n factors of the volume And so we can combine our results. Write the differential probability as a factor I'll call d phi times m I to f matrix element squared for 2e k1 to ek2 times t over the volume, where d phi is 2 pi to the fourth times an overall momentum conserving delta function times the product of the Lorentz invariant measure for each of the final state particles. Okay, so let's take a minute and understand what I've done here. So first of all, I've combined the measure we had here with the factors of 2EP from the norm of the final state. So that's this measure here. This overall momentum conserving delta function came from the numerator. That was the momentum conserving delta function in the relationship between the scattering amplitude and the matrix element. And then I have canceled off most of the factors of the volume. So let's just count those for a minute. So in the numerator, we had one factor of the volume. And in the denominator, we had two factors of the volume from the initial state and n factors from the final state. And we also had another n factors in the numerator from the measure over here. So the numerator was 1 plus n, and the denominator is 2 plus n, so that just leaves us with one factor of volume in the denominator. Okay. And so this factor d phi is known as the phase space measure. And it's manifestly, or well, maybe not manifestly, but it is Lorentz invariant. So this four-dimensional delta function is manifestly Lorentz invariant. And then we just have n copies of the familiar Lorentz invariant measure. So this is Lorentz invariant. Okay. So using the relationship between the differential probability and the differential cross-section we found earlier, we can get our expression for the differential cross-section. So just demanding that the relationship between the probability and the cross-section is the same as in classical theory, what we get for the differential cross-section is just d phi m squared over 2 ek 1 to ek2 times v. Factors of t and the volume just cancel out, which is good because they're infinite. And so for v, okay, well, so we've already seen that the phase space measure is Lorentz invariant. The matrix element is Lorentz invariant. I'm of our scattering amplitudes are Lorentz invariant, and this is just related to the Lorentz invariant scattering amplitudes by a Lorentz invariant delta function. So these two factors are Lorentz invariant. And one convenient choice of ways to define V is to let V equal the square root of K1 dot K2 squared minus M1 squared M2 squared over EK1 EK2. So this is convenient for two reasons. One is we usually have to compute K1, K2 anyways if we're computing a cross-section. The other reason is that if we define V like this, then the cross-section is Lorentz invariant. So the factors of E will cancel off, and this numerator here is manifestly Lorentz invariant. So some authors, some textbooks will use this choice. Experimentalists always use this choice. Other textbooks will define V to be V1 minus V2. These two agree as long as K1 is parallel to K2. Which is, in practice, the only case we're ever interested in. So it doesn't really matter which one you use. So if you make this choice, then the cross-section will transform as you expect a cross-section would transform. Here we're defining a Lorentz invariant cross-section. Okay. So that's the differential cross-section. And if we're interested in a total cross-section, all we need to do is perform the integral over the final state momentum. And we'll see how that works when we consider some examples later in class. But before we go and look at some examples, let's see what changes if we're interested in a decay rate instead of a cross-section. So not that much will change. But a few things will. Okay. So the first thing to consider is that if we're interested in a one-particle state decaying to a particular final state, the question we're asking is not what's the total decay rate of that particle. We're asking what's the partial decay rate of that particle. So we're asking what's the decay rate of, say, a tau to a muon and two neutrinos. So that's a question we can ask. That's different from asking what is the total decay rate of the tau. The first question is simpler, just because we only need to consider one set of final states. If we're asking what's the total decay rate of the tau or what's its lifetime, we need to consider all possible final states. So the simpler question to ask is what is the partial decay rate? And so we can relate the partial decay rate to the total decay rate. So the total decay rate, probably what you're more familiar with, which is just 1 over the lifetime, is equal to the sum over all possible decay channels of the various partial decay rates. So for tau decay, we need to consider tau decaying to muon and 2 neutrinos, and also electron and 2 neutrinos, and the various other channels. So this is the question we're asking, is what's the differential partial decay rate? And then we can always, by considering all possible decay channels, go back and figure out the total decay rate. And so not that much changes compared to what we saw before. So one thing that will change is the relationship between the probability and the decay rate. So differential partial decay rate is equal to the decay probability per unit time. And the other thing that will change is that our initial state, instead of having 2 particles, only has 1 particle. So we lose 1 factor of 2e and 1 factor of the volume. But we already lost a factor of volume in the denominator, because the relationship between the probability and the cross-section is different from the relationship between the probability and the partial decay rate. So those changes, the factors of volume, still cancel. And what we get then is that this is equal to d phi times the matrix element squared over 2ek1. And so if we have a choice, so we can define a Lorentz invariant decay rate, which is the common thing to do, or we could let it the decay rate transform as 1 over time. If we want to make this Lorentz invariant, we can just evaluate this in the center of mass. And that's the most common thing to do. And so then if we evaluate this in the center of mass, then the differential partial decay rate is just d phi. And this is precisely the same phase space measure we had before. Over times the matrix element squared over 2m1. Okay, so that.
Why would this expect that the lifetime of this part of the decay channel wouldn't be changed by a Lorentz transformation? Like if we move to isn't that?
It would be changed, but that's just special relativity. So the interesting thing is what is this quantity in the center mass frame, and it's just always common to compute it this way. As we'll see, when we're actually computing these things, it's much easier to do it in the center mass frame, and we can define these Lorentz invariant versions if we're interested in a decay rate in some particular frame. Of course, we need to boost it to figure out how long we expect the particle to live. That's always something we can do. We can just think of this as a definition of something that's Lorentz invariant. And if you look at the particle data group, which is the collection of all basically all experimental particle data experimental results, they use these Lorentz invariant measures. So you'll almost always see this one is really widespread. So everywhere in the literature, you'll see this definition. That one is more mixed. You see both. OK. So that's almost everything. About decay rates, and cross sections. There's one last thing to consider before we go look at some examples. And that's what happens if we have identical particles in the final state. So if we're computing a partial decay width or a cross section, we need to integrate over the phase space, which is equivalent to integrating over all of possible final momenta. But we can imagine that we have, say, two identical bosons in the final state. If we integrate over all possible values of the momenta, then we're double counting. There are two possible ways to avoid this double counting. One is to restrict the integration. And a second and easier in practice possibility is to divide by a symmetry factor. And this is a different symmetry factor from what shows up in the Feynman diagrams. So, for instance, if we're computing this cross-section and we arrive at this formula, and we've got two identical bosons in the final state, what's easier in practice to do is just integrate over all possible values of P1 and P2, the final state momenta, and then divide the result by 2, because we double counted. And so if we have identical particles in the final state, we'll often divide by a factor of 2 or something. And that's a different type of symmetry factor from what we talked about yesterday. OK. So the remainder of class, we'll just go through some examples and see how this works. So there are quite a few steps in actually evaluating cross-sections in practice, and useful to go through a few examples. And so the theory we'll consider is a toy model. I'll call scalar nucleon meson theory. And it has the following Lagrangian. So there is a complex scalar field, which we're going to interpret as a nucleon. So real nucleons have spin 1/2. So that's why this is a toy model. And Tibor will tell you a bit about a version of this model where the nucleons do have spin 1/2. And then we'll also have a real scalar field. Which we'll interpret as a meson. And then we'll have an interaction term. that is G rho star rho phi. So two nucleons interacting, or a nucleon and antinucleon interacting with a meson. So this is our theory. And one thing we notice when we look at this Lagrangian is that it has a symmetry. It has a U1 symmetry. If we redefine the phase of rho by some constant e to the I theta, where theta is constant. So theta is a constant. This term is invariant. The derivative doesn't see the theta. The theta can just go through the derivative. This term is invariant, and this term is also invariant. So that means there's a conserved charge in this theory. And this conserved charge will be reflected in the Feynman diagrams. So it will be useful to indicate the flow of charge on our Feynman diagrams. So before we can compute a scattering cross-section, we first need to find the Feynman rules for this theory. Okay, so let's write the momentum space Feynman rules. For the matrix element. As you saw in tutorial yesterday, Feynman rules are slightly different if we were asking a different question, say about the momentum space Green's function. So we'll write down the momentum space Feynman rules for the scattering amplitude. So the first rule is of the internal lines. And so here we have two different types of particles. So there should be two different internal lines. And one of them is a charged scalar, a complex scalar. So we should indicate the flow of charge on the line. So the arrow on the line indicates the flow of charge. And the arrow below the line indicates the direction of flow of momentum. And so this line is just equal to the Feynman propagator. And the complex scalar has mass big M. For the real scalar, there's no charge. And the mass is little m. Okay. So those are the rules for the internal lines. The other rule is for the vertex. So we have a vertex that has one phi and one rho star. So that's going to give rise to a vertex that has one dotted line and two solid lines, and with one arrow flowing in and one arrow flowing out. We know based on conservation of charge that there has to be one arrow flowing in and one arrow flowing out. Otherwise, we could certainly draw Feynman diagrams where charge is not conserved. So the vertex has to look like this. And the vertex rule is just a minus IG. So the I comes from the I in Dyson's formula. So these are the rules that change depending on the theory. And again, the rest of the rules are just that the external lines are 1. We should impose momentum conservation at each vertex. Divide by the symmetry factor. And integrate over any undetermined momenta. Yes?
I'm curious, what enforces conservation of charge when you use with your project? Because we wrote down charge like an operator. Like it's really not clear to me how that translates into like the arrows on this diagram being.
Oh, okay.
It seems that yeah.
So, that's a good question. So basically, if you recall from tutorial, we expanded, we saw how to expand the complex scalar field in terms of the creation and annihilation operators. And so we only have in our interaction Hamiltonian one particular combination of the fields. We have rho star rho. And so that's going to lead to a particular combinations of the creation and annihilation operators. And that will only be basically, we can think of it as the combination that, say, creates a particle and destroys a particle, or creates a particle and an antiparticle. So only the combinations of the creation and annihilation operators. You just that's right. You won't get the combination that, say, creates 2 particles. That would be a combination that would violate charge, and you just won't get that. That's why. Okay. Okay, so now that we've written down the Feynman rules, we can try to compute cross-section. And so just as an example, let's consider the scattering of 2 nucleons, two rho particles. Okay, so So remember, for scattering, we need to consider completely connected diagrams. So we've got, in our initial state, 2 particles. And in our final state, 2 particles. Remember, my convention is that time is going upwards. And so if we have 2 particles in the initial state, 2 particles in the final state, and we want a completely connected diagram, we need at least 2 vertices to connect everything together. So one vertex can connect at most 2 of these lines, so we need a second one. And we can try to find all the possible diagrams by first drawing all of our initial states and all of our final states, and then thinking about all possible ways to consistently connect together our vertices and our external states. So there's an obvious way to do it. If I just connect the lines as I've drawing them here. So that's one possible diagram. There's another possibility. So if I draw my initial states, final states, my vertices, so I'm forced to connect the Meson line. But instead of connecting this line to this line, I could connect it to the other line. So I can connect this one over here like this, and this one like this. And connect these two together. And so that's a second diagram we can draw. The other possibilities of connecting lines will turn out to be equivalent to one of these two. But you can draw those and move around the lines, and you commit yourself. Yes?
How come you represent that? Like, do we have an antiparticle for the nucleon?
So I'm defining the particle to be the one with positive charge. So that means that the charge is flowing upward. So an antiparticle would be something like this. So this, so for instance, if we're interested in antinucleon to antinucleon scattering, we'd have basically the same diagram, but the arrows would be going the other way. So a positive charge flowing this way or negative charge flowing that way. So this is a negative. This diagram indicates two negatively charged particles going forward in time, scattering, and then two negatively charged particles leaving. So this, if we were interested in antinucleon to antinucleon scattering, we draw this diagram instead.
From one of the vertex as close. No, we can't. A closed loop. If you're just seeing like raw to raw.
Oh, okay. So you're imagining doing something like this. So that this diagram is the same order as this one. However, it's not completely connected. So this diagram would contribute to the Green's function, but it does not contribute to the scattering amplitude. It contributes to the trivial part of the S matrix. And experimentally, it'd be very easy to distinguish that case from this case if you knew the initial momenta of the particles. So these are the only two completely connected diagrams we can draw at this order. We still need to label our diagrams. So said our initial particles have momenta K1 and K2. Final have momenta P1 and P2. And we'll have the momentum go upward. And then we can use momentum conservation to determine the meson's momentum. So if we say the meson momentum is going to the right in this diagram, then it has momentum K1 minus P1. There's now momentum K1 flowing in and K1 minus P1 plus P1 flowing out. So momentum is conserved. And similarly, over here, if we say the meson's momentum is going to the right, we have momentum K1 minus P2. Okay. So these are the diagrams. So now we can use our Feynman rules to compute the matrix element. Rho to rho. And so our Feynman rule for the vertex tells us we get a factor of minus ig for each vertex. There are two vertices here. We get minus ig squared. Then we have one internal propagator. And the momentum of the meson is k1 minus p1. So we get, so this is our answer for the first diagram. The second diagram will be very similar, except we still have two vertices and one internal propagator, one internal line. The only difference is the momentum of the meson is different. Okay. So that's our matrix element. So notice that there is no symmetry factor for either of these diagrams. There's no factor out front. But if we want to compute the differential cross-section, there is a symmetry factor in the cross-section formula. That's because our final state consists of two identical particles, in this case, two identical nucleons. So we should put a factor of a half in our cross-section formula to avoid double counting when we integrate over the final momentum. So here's our cross-section formula. And here, this m is the mass of the particles in the initial state. So this is the symmetry factor. Here, no symmetry factor. Okay. So what's left to do? So now we need to do the integrals over the final state momentum. And so a lot of this we can do in general without worrying too much about what the matrix element is. So let's look at the phase space. And I'm calling this d phi 2 to indicate that there are two particles in the final state. So this is just the overall momentum conserving delta. And then we have Lorentz invariant measure for both P1 and P2. Okay, so since our cross-section is Lorentz invariant, we can compute it in any frame we like. And a particularly convenient frame is the center of mass frame. So in the center of mass frame, it's defined if K1 plus K2 is 0, and K1 naught is K2 naught is E. Those are our initial particles, have the same energy, and same momentum. So in this case, we can evaluate some of the integrals. So what we're interested in evaluating is d phi 2 of something, and the something won't matter at all yet. So we can write this as the integral. So if we can do, say, the P2 integral using the spatial part of this delta. And if we do that, we get the following result. So first of all, 4 of the factors of 2 pi cancel. We're just left with the 2 pi squared, 2 EP1, 2 EP2. Still have the time component of the delta left over. And still doesn't matter what we're integrating, but we've set, because we've integrated using the spatial part of the delta, we've set P2 equal to minus the spatial part of P2 equal to minus the spatial part of P1, because the spatial part of K1 plus K2 vanishes. Okay. So we can go farther in general, but just to simplify the algebra, I'm now going to work in the relativistic limit. Where E is much greater than M, so that EP1 is approximately P1, which is the same as EP2 by momentum conservation. So this is 3 momentum conservation. Okay, so in the relativistic limit, yes, thank you. We can do this even outside of the relativistic limit, but algebra will just be messier. So just want to show you the simple case in class. And so we can go further. We can write the integral d phi 2 of anything as we now go to spherical coordinates for the P1 integral. We can write this as, first of all, we have a prefactor of 1 over 16 pi squared, P1 squared. EP1 and EP2 are both equal to P1. We have some angular integral. And we have now our delta function becomes a delta of 2 P1 minus 2E d. And then we have the radial integral, dP1. And whatever we're integrating, still evaluated with P2 or minus P1. And we can then do the radial part of the integral using the delta function. And we'll get a half when we do that. So remember that delta of f of x is the sum of delta x minus xi over f prime xi, where f of xi is 0. So using that here, we'll just get a half. Do the integral. So what we get is the integral d omega over 32 pi squared, whatever we're integrating, evaluated at P2 equals minus P1 equals E. And these conditions are basically guaranteed by working in the center of mass frame. So you often see this written, and because it doesn't matter what you write here, so you often see this equation written just as d phi 2 is d omega over 32 pi squared in the relativistic limit. And that's what it means.
Did you get rid of that squared on the bottom of the fraction from the measure in spherical signals?
Yes, I did, and it should have been the measure here. There should have been P1 squared here, yes. And these cancel. Okay. So you can simplify the phase space integral. And so now we can compute the differential cross-section. And so remember, we assumed that we were in the relativistic limit when we derived this. So this is not true in general if the masses of the final state particles are important. And so our formula for the differential cross-section using our result for the matrix element and this result for the phase space measure is g to the fourth over 128 pi squared, which is the square root of k1 dot k2 squared. And I'm going to make one more simplification. So I'm going to set both m's to 0. So working in the relativistic limit, where the masses of the nucleons are negligible. So real nucleons are heavier than, well, the lightest nucleons are heavier than the lightest mesons. So doesn't, in the physical application, doesn't really make sense to set this equal to 0 and not equal to, not set the meson mass equal to 0. But if you like, we can just consider the scattering in the theory where both of the masses are 0 in the massless theory. We're changing the problem slightly. I'm doing this mostly just to simplify the algebra, so I don't have to lug around all the masses. It will mean that we'll run into a problem at the end. That's related to just setting all the masses to 0, but I'm really doing it just to illustrate the procedure. This theory is not particularly realistic anyways, so I just wanted to show you how the calculations work, and we'll make this simplification of the algebra. So in that case, then our matrix element squared just becomes 1 over k1 minus p1 squared over k1 minus p2 squared. Okay, so the last thing left to do is just evaluate the products of momenta. So we're in the center mass frame. So K1 is EK. We're in the center mass frame and everything is massless. And K2 is equal to E minus K. P1 is equal to E P, and P2 is equal to E minus P. Also, since everything is massless, K is equal to P, 1 and 2 is equal to E. And K1 squared is equal to K2 squared is equal to P1 squared is equal to P2 squared is equal to 0. Okay. The last thing we need is the angle between P and K. So we can imagine that K and the two particles are coming in momentum K and minus K. They collide, and then they go off with momentum minus P and P. And let's just denote the angle between P and K as theta. Okay, so what's left to compute? So in this term, we'll have a dot product of K1 and P1. And we can evaluate that straightforward manner. So we get E squared minus P dot K, which is E squared minus E squared times cosine of theta. And this term we have K1 dot P, which is the same, except we've got a plus sign here. So we get an E squared 1 plus cosine theta. And finally, this term, which came from the velocity, is a K1 dot K2, which is E squared plus K dot K, which is 2E squared. And so putting these results together, we get our differential cross-section. E sigma d omega is g to the 4th over 256 pi squared e to the 6th. We plug these results in here. The k squared and the k1 squared and p1 squared terms cancel. Similarly, over here. Yeah, also they're 0. They're just 0. And so if we combine these two terms, what we'll get is this expression. And this is as far as we can go. If we hadn't said both the masses is 0, we'd have a more complicated expression here that we could do the integral. We're stuck now because the cosine integral diverges. That's related to taking the massless limit. That's our first result for the cosine. All right, so that's our first cross section. Last part of class, I just want to talk about a second related cross section. We won't have to go through nearly as much. As we'll see, it's closely related. Just imagine instead of scattering two nucleons, scattering a nucleon with an antinucleon. So what are the diagrams? So again, my strategy is first draw the external particles. So we've got one nucleon, one antinucleon in the initial state, one nucleon and one antinucleon in the final state. Again, we need two vertices to connect them up. And there are two possible ways to connect our external lines to the vertices. There's this one. And there's also this one. At leading order. And the momentum of the meson in this case, if it's going to the right, is just K1 minus P1. Which is the same as we had before. But over here, we see something different. So in this case, we have the matrix element rho, rho star to rho, rho star is, again, we've got two vertices in each diagram. One propagator, one internal line. So first diagram is the same as before. And the second diagram is almost the same as before. We just have different momenta for the meson. Okay, so this result is very closely related to what we saw before. And in fact, there's a relationship we can write down between the matrix elements. So in particular, you see that the matrix element we calculated before, where we had two particles scattering to two particles. Is equal to the matrix element we have now if we make the replacement that if we exchange P2 with minus K2, and we get the same thing as we had before. So we have the same result if we exchange both directions. Consider the scattering of, so the matrix elements are the same if we make this replacement P2 goes to minus K2 and vice versa. So these two matrix elements are the same. And this is an example of a general relationship between matrix elements. It's known as crossing symmetry. Crossing symmetry is a symmetry of the S matrix that in general says that if we have a matrix element with some particle in the initial state, some other set of particles, scattering to some final set of particles that's equal to the matrix element, where you keep the rest of the initial state the same and the rest of the final state the same, but move phi with momentum p, replace phi with momentum p in the initial state with the antiparticle of phi with momentum minus p in the final state. So this is the antiparticle of phi. And for a real scalar, phi bar is equal to phi. For complex scalar, phi bar is equal to phi star. So why is this true? Yes.
Define conditions to write the second diagram. The arrows are all in the bottom are all go up.
Oh, thank you. This should be down. So why is this true? So let's just draw a picture of the Feynman diagrams in the two cases. So in the first case, we've got some other set of particles. They interact in some way. The rest of the diagram we're leaving the same. But then there's some part of the diagram where some of the particles interact with the particle phi there, which has momentum p. And these are some other set of particles that have, say, momenta q1 up through qn. They could be charged or uncharged. It doesn't really matter. I'll draw any arrows on them. And so what the statement of crossing symmetry is saying is that this diagram is equal to the same diagram where I keep everything else the same. The same set of particles interacting with this particle phi, but now phi is an antiparticle in the final state. And these two diagrams are the same because the Feynman rules we'd use to write down the expressions for these diagrams are precisely the same. So momentum will still be conserved at this vertex, and our Feynman rules don't care at all about whether we have this phi in the initial state, momentum p, or phi bar in the final state with momentum minus p. It also works for fermions. It works in general, but yeah, it should be clear for scalars because it's a little less clear for fermions. So you'll learn about that from TIPRA. But for scalars, we just write down exactly the same expressions for these two diagrams. So this is a powerful relation in studying scattering amplitudes. Relates two different scattering amplitudes. One comment, though, is that the kinematics between the two are in general different. So just because there's this relationship between crossing symmetry relationship between this scattering amplitude and the scattering amplitude we computed in detail before does not mean that the cross sections are the same. The kinematics are different. What we worked out for the relationship between the momenta and the integrals over phase space, those can be different, and usually are different in general. And sometimes, if you use crossing symmetry, one side might be kinematically allowed and the other side might be kinematically forbidden. What I mean by kinematically forbidden is that an example of a kinematically forbidden process is, say, a particle decaying to a set of particles which have a larger total mass than the initial particle. That just can't happen. That's kinematically forbidden. But it is a powerful relationship. And so scattering amplitudes and decay rates are how we relate the results of our calculations to experiments, at least in particle physics. So they're an important check for going from theoretical manipulations to the data. And it's extremely successful in particle physics. As you know, the Standard Model is one of the best tested theories of nature we have. So that's scattering cross sections and decay rates. And so what we're going to do tomorrow is look in more detail at what happens beyond linear order. So today, all of our calculations were at tree level. Basically, at leading order in perturbation theory, there were no loops in any of our diagrams. And several new and interesting things happen when we do consider loops. So I won't have time to go through all of the new and interesting things, but I'll touch on many of them, and you'll see those in more detail in QFD2. Any questions on this? See you this afternoon.